Good morning everyone. In the previous classes we developed interpolating polynomials at a set of discrete points which are equally spaced. We used the concept of forward and backward differences and developed these interpolating polynomials. Now we will see how we can obtain interpolating polynomials which interpolate a given function at a set of discrete points which need not be equally spaced. And Lagrange developed this interpolation formula and it is referred to as Lagrange interpolation polynomial. In this case, the nodes xi need not be equally spaced. So, let us consider y equal to f of x to be a function which takes values f of x naught, f of x1, etc., f of xn corresponding to the points x naught, x1, etc., xn, that is points xi where I is equal to 0, 1, 2, 3 up to n. As I said earlier, the xi's need not be equally spaced. So, there are n plus 1 distinct points. Therefore, we can represent this function y equal to f of x by an interpolating polynomial of degree at most n, say p n of x. So, we shall write down the form of p n of x as a naught into x minus x1 into x minus x2 etc. x minus xn plus a1 into x minus x naught into x minus x2 etc. x minus xn plus a2 into x minus x naught into x minus x1 into x minus x3 and so on x minus xn plus etc. plus an into x minus x naught into x minus x1 etc. up to x minus xn minus 1. We observe that the first term has n factors x minus x1, x minus x2 etc. x minus xn. The coefficient is a naught. This does not contain the factor x minus x naught. The second term again has n factors x minus x naught, x minus x2, x minus xn. It does not have the factor x minus x1. The coefficient of this term is a1. So, we now know the pattern. So, that the last term has again n such factors x minus x naught, x minus x1 etc. x minus xn minus 1 and does not have the factor x minus xn in it, and the coefficient of this term is an. So, there are n plus 1 unknowns a naught, a1 etc. an, and we want this polynomial p n of x to be the interpolating polynomial that interpolates the function y equal to f of x at a set of discrete points xi. Namely, we want p n of x to be such that p n of xi is f of xi for I is equal to 0, 1, 2, 3 up to n. When we satisfy these n plus 1 conditions, we will determine the constants a naught to a n, and when we substitute them here, we will obtain the required interpolating polynomial. So, let us work out the details. So, I want p n of x naught to be f of x naught, which says f of x naught is equal to, I observe that all these terms have x minus x naught as a factor in them. So, when I evaluate at x is equal to x naught, all of them will not contribute. The only term that contributes is the first term. So, that gives a naught into x naught minus x 1 into x naught minus x 2 etc. up to x naught minus x n, which tells us that a naught is f of x naught divided by x naught minus x 1 into x naught minus x 2 etc. up to x naught minus x n. So, a naught gets determined using this condition. Similarly, I apply the next condition. What is it? P n at x 1 must be equal to f of x 1. So, this tells me that f of x 1 should be equal to, again I have to evaluate the right hand side at x is equal to x 1, and I observe that except this term, all the other terms have x minus x 1 as a factor in them, and hence they will not contribute. The only term which contributes from the right hand side is this term, and that gives you a 1 into x 1 minus x naught into x 1 minus x 2 etc. up to x 1 minus x n, and therefore, a 1 is f of x 1 divided by x 1 minus x naught into x 1 minus x 2 etc. up to x 1 minus x n. So, we have determined a 1 from the condition P n at x 1 is f of x 1. Similarly, a 2 will be obtained using the condition P n at x 2 is f of x 2. So, in general a I will be obtained using the condition P n of x I equal to f of x I. So, let us just write down the result for a n. So, we obtain a n by using the condition that P n at x n is f of x n. So, this gives you that a n will be equal to f at x n divided by x n minus x naught into x n minus x 1 etc. up to x n minus x n minus 1. So, having determined all these coefficients, we can substitute in P n of x equal to a naught into something and so on plus a n into this factor, and write down the resulting interpolating polynomial. Hence, P n of x will be equal to a naught. What is it? It is f of x naught by this factor multiplied by x minus x 1, x minus x 2 etc. x minus x n. So, we shall write down the term as follows. So, it is x minus x 1 into x minus x 2 etc. up to x minus x n divided by the denominator is x naught minus x 1 into x naught minus x 2 etc. up to x naught minus x n multiplied by f of x naught. That is the first term. Next term will be plus. I should substitute for a 1. So, a 1 is obtained here. When I substitute, I get x minus x naught into x minus x 2 etc. up to x minus x n divided by x 1 minus x naught into x 1 minus x 2 and so on x 1 minus x n multiplied by f of x 1. And we write down the other terms, and finally, the term a n, which will be given by x minus x naught into x minus x 1 etc. up to x minus x n minus 1, which appears here, that multiplied by a n, and a n has been obtained as this. So, we have x n minus x naught into xn minus x1 etc. up to xn minus xn minus 1 multiplied by f of xn. We observe from here that the numerator does not have the factor x minus x naught in it, and the denominator is such that wherever x appears in the numerator, it is replaced by x naught in the denominator, and the first term is multiplied by f of x naught. Similarly, the factor x minus x1 is missing in this term, and the denominator is such that wherever x appears in the numerator, it is replaced by x1, and the term is multiplied by f of x1. And similarly, the last term, the factor x minus xn is missing, and wherever x appears in the numerator, it is replaced by xn. So, we have xn minus x naught etc. up to xn minus xn minus 1, and this is multiplied by f of xn. And this is the required interpolating polynomial, which has the property that Pn of xi equal to f of xi, where the xi's need not be equally spaced. So, we can write down this polynomial in the form L naught of x into f of x naught plus L1 of x into f of x1 plus etc. plus Ln of x into f of xn, where we shall write down what Lk of x is. So, Lk of x is such that L naught of x does not have the factor x minus x naught, L1 of x does not have the factor x minus x1, and so on. So, Lk of x will not have the factor x minus xk in it in the numerator. So, it will have x minus x naught into x minus x1 etc. x minus x k minus 1 into x minus x k plus 1 etc. up to x minus xn. What about the denominator? In the first term, when x minus x naught is not present, wherever x appears, it is replaced by x naught. So, here x minus xk is not present. So, wherever x appears in the numerator, it should be replaced by xk. So, it is xk minus x naught into xk minus x1 etc. xk minus xk minus 1 into xk minus xk plus 1, and so on xk minus xn, and that is what is Lk of x, and it should be multiplied by f of xk, so that we have Pn of x to be equal to L naught of x f of x naught plus L1 of x f of x1 etc. Ln of x f of xn, and therefore, I can write down Pn of x in the form sigma k is equal to 0 to n Lk of x into f of xk. And let us look at the properties of this Lk of x, right. What can you say about Lk at xk? So, when I evaluate at x is equal to xk, then I will have xk minus x naught, xk minus x1 etc. up to xk minus xn, and I observe that these are the factors which appear in the denominator. So, Lk of xk will be equal to 1. On the other hand, if I evaluate Lk at any other xi I not equal to k, then I observe, I put x is equal to xi, right, and in that case there will be a factor x minus xi here in the numerator, and therefore, this will be equal to 0, and so whenever k is different from I, Lk of xi is equal to 0. Hence, we have the Lagrange interpolating polynomial to be given by this with the property that Lk of xk is 1 and Lk of xi is 0 for k not equal to I. And this polynomial is the interpolating polynomial that interpolates the given function y is equal to f of x at a set of n plus 1 distinct points which need not be equally spaced. and this is a polynomial of degree at most n, which interpolates at a set of n plus 1 distinct points. So, the natural question that comes to our mind is this polynomial a unique polynomial that interpolates the given function at a set of n plus 1 distinct points. So, let us prove that the polynomial is a unique polynomial that interpolates the given function. Let us work out the details of this. So, we want to prove the uniqueness of the Lagrange polynomial which interpolates the given function. Suppose on the contrary, there is a polynomial Qn of degree at most n, which interpolates the function y equal to f of x at xi for I is equal to 0, 1, 2, 3 up to n, where xi's need not be equally spaced, and that Pn is different from Qn. Then we observe that Pn minus Qn is a polynomial of degree at most n, and in addition Pn of xi minus Qn of xi is f of xi minus f of xi, which is 0 for I is equal to 0, 1, 2, 3 up to n. Why? Each is an interpolating polynomial for the function f of x that interpolates the function at the interpolation points xi for I is equal to 0 to n. Since a polynomial of degree at most n cannot have n plus 1 distinct roots, it is identically 0. So, Pn minus Qn is such that this is identically 0, which implies that Pn of x is equal to Qn of x, which is a contradiction to our assumption that Pn is different from Qn, and therefore, our assumption is wrong, and then there exists only one polynomial Pn of x of degree at most n that interpolates the function at a set of n plus 1 distinct points, and that completes the uniqueness of Lagrange interpolation polynomial that interpolates the given function at a set of discrete points. So, let us complete the details. So, which is a contradiction to our assumption that Pn is different from Qn. Therefore, there exists only one interpolating polynomial, that interpolates the function f of x at n plus 1 distinct points. So, I can also say there exists only one interpolating polynomial of degree at most n that interpolates the function f of x at n plus 1 distinct points, and this completes the uniqueness of the interpolating polynomial, namely Lagrange interpolating polynomial that interpolates the function at a set of discrete points. So, let us understand the result by taking an example. Suppose say I want you to construct a quadratic interpolating polynomial that interpolates the function f of x is equal to e power x in the interval -1 to 1 with interpolation points. How many points should I have if I want to interpolate the function by a quadratic interpolating polynomial? That is a second degree polynomial. So, I require 3 interpolation points. So, the interpolation points are say x naught equal to -1, x1 equal to 0 and x2 equal to 1. Then what are the corresponding values of this function f of x naught? It is e to the power of x naught. F of x1 is e to the power of x1 and f of x2 is e to the power of x2. So, I have information at a set of 3 distinct points x naught, x1, x2 and the corresponding function values are available too. Therefore, I can represent this function in the interval -1 to 1 by a quadratic interpolating polynomial, which we denote by P2 of x. What is that P2 of x? It is L naught of x into f of x naught plus L1 of x into f of x1 plus L2 of x into f of x2. And hence, I write down what are these polynomials L naught, L1 and L2. What is L naught of x? It should be x minus x1 into x minus x2 by x naught minus x1 into x naught minus x2. So, it is x minus x1 is 0, x minus x2 is 1, then x naught is minus 1, then x naught is minus 1 minus x2 which is 1. So, that I get x into x minus 1 divided by minus 1 into minus 2. So, it is 2, that is L naught of x. Similarly, we write down L1 of x. So, that will have x minus x naught into x minus x2 by x1 minus x naught into x1 minus x2. So, that gives us x minus x naught is minus 1, x minus x2 is 1 and x1 is 0, x naught is minus 1, x1 is 0 and x2 is 1. This gives you x plus 1 into x minus 1. So, x square minus 1 by 1 into minus 1. So, we have 1 minus x square, that is L1 of x. We now write down L2 of x. This will be x minus x naught into x minus x1 by x2 minus x naught into x2 minus x1. We substitute the values for x naught, x1, x2. So, x minus x naught is minus 1, x minus x1 is 0, x2 is 1, x naught is minus 1, x2 is 1 and x1 is 0. This gives you x plus 1 into x divided by 2 into 1. So, we have determined L naught, L1 and L2. We also have knowledge of f of x naught, f of x1, f of x2. We substitute and obtain the quadratic interpolating polynomial P2 of x that approximates the given function e to the power of x in the interval -1 to 1. What is it? P2 of x will be x minus x into x minus 1 by 2 into f of x naught, which is 1 by e, plus L1 of x 1 minus x square into f of x1, which is e power 0, then plus L2 of x, which is x into x plus 1 divided by 2 into f of x2, which is E. So, this is the required quadratic interpolating polynomial such that P2 of x approximates the function f of x. What is f of x? E power x is approximated by P2 of x, where for x in the interval minus 1 to 1. I hope the explanations and the calculations are clear to you. So, we have been able to obtain an interpolating polynomial known as Lagrange interpolating polynomial that interpolates the function at a set of n plus 1 distinct points which need not be equally spaced, and the polynomial is of degree at most n. And this polynomial has the property that at the points xi, it takes the same value as the function. So, this is so for I is equal to 0 to n. So, the question arises, what happens at any other x which is different from xi for I is equal to 0, 1, 2, 3 etc. up to n. At these points x which are different from xi, Pn of x will be different from f of x. So, the question is, how large is this difference f of x minus Pn of x at any x which is different from xi? So, if the function f has sufficient smooth properties, then it is possible to provide an estimate of the size of the interpolation error. What is the interpolation error? At any x, the difference between f of x and the polynomial of degree n that approximates the function is f of x minus Pn of x, and that is the interpolation error. If f has some smooth properties in an interval, then it is possible for us to provide an estimate of the size of the error bound, and that is given by the following theorem. So, we shall write down the statement of the theorem and then try to work out the details of the proof and obtain an estimate of the size of the interpolation error when a function f of x is approximated by a polynomial of degree at most n with interpolation points xi, I is equal to 0 to n, which need not be equally spaced.